All right. Hi, everyone. Um, I'm glad to see that people are still here um, and not endlessly working on their assignments. Um, so that's good. It's the last hour of the semester. I'm sure everyone's tired, and so I'm glad people are still here. Anyways, yeah. So as I said, this week I'll probably try to do a recap of the semester. Okay. If there's any questions for this week, feel free to let me know. Yeah. So if there's any questions from this week, feel free to let me know. I assume one of the most difficult questions is this question here. Okay, it's representation learning is necessarily more flexible than fixed representation, right? And this is false. And this kind of seems counterintuitive, right? Especially because representation learning, you're learning how you represent your data set, right? You're learning how you're learning more complex, or you can learn more complex ways of representing your data set. Okay. So why is this false? So it's very simple. Because representation learning, you also need to learn the number of representations. Okay, so if we think about a neural network, which is the most simplest, right? So we're taking, let's say, 5 inputs. Okay, so this is my layer. Okay, my first layer, I have 5 inputs, right? So the fixed representation has five representations, I guess. Right, we consider representations, right? Because representations is kind of like a very fancy word, right? It's very complex. But it's very simple, right? So if you think about a house, right? If you think about a house, and what you want to do is you want to decompose the house into its properties, right? So a window would be a way to represent the house, right? So the number of windows is a property of the house, and that's one way you can represent the houses, right? The bathroom area, so like the square feet of a house. This is a parameter. This is a attribute of the house, and you can use this to represent the house, right? And of course, so that's essentially what a representation is. That how do you choose to represent the data set? Okay, is that you can use the number of windows, the square foot area, the age of the house, and so on. Okay. Then when you're learning representation, okay, so then we can learn as many representations as we want, right? So we can do, this is 1, 2, 3, 4, 5, 6, 7. Right, so we have, right? So 1, 2, 3, 4, 5 inputs gets fed into the second layer. And let's say we're doing classification, right? So we have one output, right? And this is our output. So we effectively are learning seven different representations of the data set, right? So we're learning 7 different ways of representing a house, and each one is going to be different from the other thing. Okay, so that's essentially a representation, right? It's a very fancy name. Okay, I guess this should be 7, but lots of arrows. Okay, but right, so representations. So even when you hear math, so when they say representation theory, that's all it is. Okay, is that representation is how do you want to describe your data set, or how do you want to describe your object? Okay, you can describe it using multiple ways, right? So in email, you may represent the object as number of the time the email was sent, who it was sent by, stuff like this. Okay, and that's all representation is. And then when you're learning representations, you're just learning different ways of looking at the data set. Okay. Anyways, so here we're learning 7 representations. So this will be more flexible, right? But who said we have to learn more representations, right? In theory, we could just learn. We could just learn one representation, right? So instead of it being from like a 5 to 7 to 1, right? Instead of the network being 5 to 7 to 1, we can make the neural network be 5 to 1 to 1. Okay, 1, 2, 3, 4, 5. and it goes to one node, and this is the output. One. Right, and in this case, the representation is only one number. Okay, so you're only choosing to represent houses using one feature, essentially, one representation. Okay, so of course, in this case would be less flexible, right? Because you need enough representations of it, right? So you need essentially the dimensions. Okay, so you need to represent your data set enough so it's accurate. Okay, but that's the reason why representation learning is not always flexible, because if you choose to only use few representations, so you only use one representation, it can be less flexible. Okay, so PCA is another example, right? So principal component analysis. This is also representation. This is like more or less representation learning. And all you're doing is that you're just representing your data sets in a different way. Okay, so this week we were looking at the credit card data set, and it's you do the PCA transformation, so it's all anonymized, right? Right, but that's representation learning. Okay, so very cool idea. Okay, and representation, even representation theory. Okay, they sound really fancy, sounds really complicated, but that's all it is that you have an object. Okay, and how do you want to represent that object? Do you want to represent that object using the number of windows, the number of wheels, like its car maybe, the manufacturer, stuff like this. Okay. Yeah. Okay. So we'll leave it like that. Okay. Yeah. Okay. So I just assume people will have a lot of. I assume people has a lot of questions on this. So that's that. Okay, but if there's any other questions, feel free to let me know. Otherwise, we'll just move on to the we'll move on to the review of the course. Okay, cool. Okay, so I assume there's no questions. So let's start the review. So there is a lot of material this course, right? There's the lectures, there's my recorded tutorials, and there's also the weekly Q&A. Okay, so there's a whole bunch of things for you to watch. And all that I'm doing here is I'm just going to give you kind of like a really quick overview of the course. Okay, and if you want more details, I suggest you either watch the tutorials or watch the recorded Q&A, right? Because in some tutorials, I actually go quite in depth of some of the methods, right? So the generalized additive models, I go in quite details of the backfitting procedure. Okay, so if you do want more in depth, I suggest you go to the Q&A session, watch the Q&A recordings or the tutorials, and they'll give you more things. Okay, and really you should think about this as kind of there will not be consultations next week. Yeah, there will not be. But at least for right now, that's all I know, is that there is no consultations next week. But we'll be on ed, and we'll keep answering questions and stuff like that. Okay, so there's that. Yeah. Yeah. Yeah, so try to think about this as me just giving the brief highlights. So I'm not going to go into too much details about things. I'm just going to show you like the key features of the course. Okay, so let's start. So for the first week, we're kind of introducing machine learning methods, right? And we have three main types of learning, right? So supervised learning, unsupervised learning, reinforcement learning. Okay, and we should know the difference between these two, right? So supervised learning, you have the X variable and you have the Y variable, right? So in supervised learning, you have the target variable and you're trying to predict the target variable. Okay, so you should think, or at least I like to think about supervised learning as kind of, it's a textbook, okay, and you have the answers to every single question, right? And what you're trying to do is that you're trying to build a pattern between the questions and the answers, right? And that will be supervised learning. Unsupervised learning would be kind of, you were just given the answers, right? And you were just given the questions, but you weren't given the answers. Okay, you just need to like group similar questions together, right? Maybe you group all the multiplications together, you group all the additions together, the divisions together and stuff like this, right? So that would be unsupervised learning, is that you typically don't have the target variable, and all you're trying to do is you're trying to find interesting patterns in the data set. Okay. Then you have reinforcement learning, which is the most interesting one of these three. And reinforcement learning is kind of like you want to do something. Oh, okay, let me just, right. So supervised learning, we have an input and output pair, right? So the input, right, so the input and the targets, right? And unsupervised learning, we just have the inputs, and the whole point is to find interesting patterns. Oh, I don't think I said this. But one of the best examples of clustering is if you use hang on, let me wait, hang on. Okay, I can't find it anymore. Okay, I can't find it anymore. So yeah, I'm not gonna. All right. And then we have reinforcement learning, right? In reinforcement learning, we kind of have we have a learner. Okay, we have a learner, and what it's trying to do is it's trying to maximize some sort of reward. Okay, and this is really, really kind of general, right? It's not really satisfying. But essentially, you can sort of think about it as a lightning, right? As which I said in the first week, is that you have a lightning, and your goal is to start from the beginning, and you try to find your way throughout the sky to reach the bottom. Okay, and what you do is that you're trying to find the actions to maximize your reward, or to maximize your reward there. Okay, and playing games is the best example. Playing games is the best example of this. Now, artificial intelligence is in artificial intelligence, all you're trying to do is you're trying to generate fake intelligence, right? That's what it is, right? Is that, we have natural intelligence, I guess, right? Because we were born with it, more or less. And artificial intelligence, we're trying to create intelligent design. Okay, we're trying to create machines that can think by themselves. Okay, they can think by themselves. And right now, at least, the only way we can do this is through machine learning. Okay, so that's why we consider machine learning is a subset of artificial intelligence, because artificial intelligence, we're trying to make machines learn by themselves or think for themselves. And right now, the only way we can do this is through machine learning. Okay, and then thinking, in this case, thinking would be the training, right? So we can train your models by gradient descent or something like this, or you minimize the cross-validation error. That would be considered the learning phase. Right, and of course we have classification and regression, right? Two main types of supervised learning. We have observations, cases, and so on. Make sure you know how to do your matrix multiplications. Okay, so what I was going to say in the beginning, so I showed this last semester. I'm not sure if I showed this semester, but one good example of clustering, so unsupervised learning, is that when you want to buy shirts from different consumers. Okay, so you have medium, small, large, and extra small, extra whatever, right? Extra medium, whatever. The way that you actually do these is that these are your groups, right? So you want mediums, so you want small, medium, large. Okay, so you want to find 3 clusters in your data set, right? So or you want to find three clusters in your data set. And the thing is that each company will have their own data sets. Okay, so that's why, at least from what I hear, is that for female clothing, if you buy from a different brand, you can actually get different, like mediums are different from different brands. And the reason why is that different brands have their own data sets. Okay, and so when you cluster on it, the centroid, okay, so the cluster tends to be different. Okay, but very cool application of clustering. Okay. Okay, so anomaly detection is I guess, I don't know. Okay. So these are some other unsupervised methods. So, clustering recommender systems, so recommending people shows, I guess that's kind of that. Okay, and we also have structured and unstructured data sets, right? So we have structured data sets, which are basically numbers, dates, and strings. So strings are words. And unstructured data sets are images, audio, videos, emails, spreadsheets. Okay, so you have numbers and dates and strings, and we have images, audio, videos, and so on. Okay, and importantly, neural networks works well on unstructured data sets. Right, so neural networks work well on this, but don't work so well on this one. Okay, and in contrast, linear regression, trees, XGBoost, all these models tend to work better on structured data sets, but not so well on unstructured data sets, right? Yeah, exactly. Okay, so these perform better on structured, but neural networks tend to perform better for unstructured. Okay. And we're mostly focusing on tabular data sets, right? So number, dates, and strings, of course. Okay, so that's week one. Okay, so this is week two. So this week we started with supervised learning, right? So we have input and output pair, and we're doing regression. So these are some examples of this, right? So very important, what is a training set? What is a validation set, right? And why do you use a validation set, right? Is that we train the models on the training set, but maybe you have some hyperparameter of your model, right? So for k nearest neighbors, right? You need to find the optimal number of k. The way you do that is by looking at the validation set to find the optimal value of k, right? Right, and a metric is a way to measure the quality of your model, right? So the mean squared error, the mean average deviance, the accuracy of the model, the ROC curve, area under the curve, precision, stuff like this. These are all metrics, okay? Right, mean squared error is most common for thing, and we commonly report the root mean squared error because it's on the same scales as the response, right? So if we think about y, if y is prices, then here you're taking the square of the prices, right? So that the error would be prices square, not price. And so you take the square root, so it's now just price, okay, not prices square. R2, so yeah, mean average, mean absolute error. Right. And of course, the key is that we want models that can generalize well, right? Is that we don't care so much how well it does on the training set, but we care about predicting on outside of the data set. Okay, so on this generalization capabilities outside of the data set. And we do that, right? So we do that by using the validation set, right? So the validation set is basically a proxy for the generalization error, right? Meaning that we use the validation set to basically approximate the generalization error, right? Yeah, approximate the generalization error. Right, and here we have linear regression. Okay, so here you have linear regression, and the least squares algorithm means that we're going to find the coefficients such that it minimizes the squared error. Okay, such that it minimizes the mean squared error. Okay, and this will be known. This is known as the ordinary least squared method. Okay, so the OLS is basically just this equation here, right? The mean squared error between the model and the target variable. right? And it can be shown that the OLS has a solution, and it's that, right? And we can prove this is a solution by finding the first derivative, setting the first derivative equal to 0, and then we can prove it's a minimum by setting the second, by looking at the second derivative, right? And so on. Okay. Right. Now, linear regression has good computational speed, right? And, in the beginning of the course, we hear computation speed and we're like, okay, whatever, right? But now that we're learning neural networks, we're learning gradient boosts, stuffs are taking, 10, 20 minutes. Computation speed is really useful, okay? So computation speed is very, very important. Okay, and then here, there is like a very, there is a lot of intricate, kind of stuffs here. Okay, so like the classic assumptions of linear regression and stuff like this. Okay, so I'm not going to go through this because it's I need to be a little bit more kind of like careful with this. Okay, but there's some notes on the linear regression thing. So if you're confused with the difference between supervised learning and how this differs from the classical assumptions of linear regression, you can just read this thing here. Okay, it's just the week 2 Q&A session. Okay, so that's if you're confused with what we do in supervised learning versus using this kind of classical assumptions. Okay. Okay. And of course we can, why do we take the log transformation of a variable, right? So this is a pretty good question we can ask, right? Why bother taking the log transformation of a y variable, right? Because it removes, it reduces skewness of the errors, right? It stabilizes the variance and addresses nonlinearity, right? So 3 reasons why you might want to transform your y variable. Okay, and this is if you have, okay, and we have k nearest neighbors, right? So k nearest neighbors, all you're doing is that you're just what am I trying to say? You just take the average of your neighborhood. Okay, and it's important that you know how to make your predictions here, right? So let's just say that your salary. Okay, I'm not going to think too hard here, but let's say your training, your data point is that your salary is equal to, let's say, 10,000. Okay, 10,000. So you look at your nearest neighbors. Let's say k is equal to 2, right? So we're doing k is equal to 2. So we look at our 2 closest neighborhoods. So that will be this one here, right? And that will be this one here. Okay. Yeah, that's the 2 closest to us. Then we take the average of this one and this one, right? So our prediction would be 576 plus 1357 divide 2. Okay, so that's how you would that's how you would make the predictions for k nearest neighbors, is that you just look into a neighborhood and you just take the average of the y variable, okay, of the sales. Important. Okay, so yeah, just don't accidentally take the average of salary. Okay, make sure you're taking the average of the y variable. Right, hyperparameters. So hyperparameters by definition are not trainable. Okay, so basically, more or less what this means is that hyperparameters, you cannot take the derivative of this, right? So you can't do like stochastic gradient descent, or you can't use the first order conditions and stuff like this. Okay, so that's basically it, is that they're not trainable. Okay. And here we have some distance functions, right? So we have the Euclidean distance, the Manhattan-Loss distance, right? And know the difference between k nearest neighbors and linear regression. Know the difference between linear regression and k nearest neighbors, right? Linear regression is very fast, high interpretable, low variance, right? But k nearest neighbors, it's high flexible, so different from linear regression. It's not very smooth. It's very memory intensive, so there's a lot of data points you need to remember. It can be slow, stuff like this, right? And you also have cursor dimensionality. Okay, so just make sure you know the positive, like, for a given model, make sure you know what's good and what's bad about it, right? Yeah, make sure you know what's good and what's bad about that. So EDA is then the process of just plotting your data sets. Okay, so just plotting it. Right, and just be careful, right? So we have 4 different types of data sets here. We have discrete data, we have continuous, nominal, and ordinal, right? So be very careful between nominal and ordinal, okay? Because nominal does not have any order to it. Okay, so color has no order to them, but something like ordinal data has order to them, right? So always, usually, sometimes, rarely, never, right? This has an order to them. Okay, so you can rank them. Discrete data is you can count it. Okay, so you can count, but you can't count always. How many numbers is always, right? Right? How much numbers is always, right? You can't count that. So make sure you know your difference. Right, so these are different ways you can measure dependencies. Probably not really useful to remember all of them. Okay, yeah. So feature engineering is a process of creating new features, right? So looking at illegal downloading sites to determine which TV shows you will purchase next year. Okay, creative feature engineering, right? Very, very important. Right, so make sure you experiment. Okay, that's not very useful. Right, and so this is the representation theory that we're talking about here, right? So again, so this is a polynomial representation. Okay, so what this means is that, let's say you have a house, right? So you have a house and you want to use windows. You say x is equal to windows, right? So you have one feature that's windows, right? And in this polynomial representation, what this means is that you have one feature which is windows. Your next feature is going to be windows squared. Okay, so the next feature is just the square of your windows, right? Right, and this is a different representation to this one, right? It's a different representation because now you're not looking at windows, but you're looking at the square of the windows, right? May that be useful? I don't know, but that's all representation. Representation is that different ways of looking at the data set. Okay. Yeah. Right, so feature engineering versus representation learning, right? So feature engineering would be more so like, the fixed representation, right? Because where we're choosing that representation, right? So we're choosing which features to choose, right? So we're choosing that representation, okay? And then we just leave it there. And then representation learning would then be, we're actually learning how to represent that data set, okay? And again, representation is nothing magical. All it's saying is that, how do you want to look at your data, right? How do you want to represent that data set? You have a house. How do you want to represent a house? By the number of windows, the square foot area, square of the windows, right? Who knows? Okay. And of course, different representations will work better than others. Okay, so when you're doing different encoding types, so GLMM encoding, one-hot encoding, stuff like this. These are all different representations. Right, make sure you know standardization, right, where you subtract the mean divided by the standard deviation, and min-max scaling. Make sure you know the difference, right? Min-max scaling makes everything between 0 and 1. Okay. Right, and again, it's very important to do feature scaling when you're doing regularization, right? So when you're doing ENet regularization, lasso regularization, stuff like this, you need to make sure you standardize your data set. Okay. And the log transformation is effective to reduce right skewness. Okay, so if there's if there's a right tail, log transformations is good to remove this. And there are more general transformations which can fix, I guess, both left skew and right skew. Okay, and these will be Box-Scott transformations and Yo-Johnson transformations. Okay. Right, and yeah, so one-hot encoding again is a representation of your data set. Okay. Dummy encoding again is a representation. Like cardinality target encoding. Oh yeah. Also, so if you have, a question you can have is that you have a variable, you have a categorical variable that has a lot of features. Okay, how do you fix this? Well, you fix this, well, one way you can fix this is you can use target encoding. Oh yeah, you can merge sparse categories, do hash encoding, target encoding. Okay, and then when you're talking about target encoding, what's good about target encoding and what's bad about it? Well, what's good about target encoding is that you can reduce the dimensions, right? So if you have a lot of categories, target encoding reduces the number of dimensions, right? Sorry. Yeah, you're not using as many dimensions. Okay, but the issues with target encoding is that you can have target leakage, right? That information from the Y variable can now leak into your data set. Okay. Right. And interaction effects. So, right, interaction effects means that there's some sort of interaction between X and 2. Okay, if you just have F, so if you have X1 plus X2 plus X3, this is additive. So there's no interaction effects. Interaction will occur when there's like a multiplication between them two. Okay, so that'll be an interaction effect. Right, and again, this is again just a representation, right? So if you have windows, oh yeah. So we have windows, and let's say we have the doors. Okay, we have the number of doors. Okay, then we can add another feature, which is the windows multiplied by door. Okay, so this will be another way to represent the houses. Okay, but how useful this representation is, I'm not sure. Okay, but again, this is just a representation. Okay, and that's all representation theory is that stuff like that. Okay, and how can you deal with outliers? You can delete them, you can censor them, you can transform them, you can create a dummy variable. Okay, censor meaning that it's explained more concretely in the actual lectures, but censor meaning that you basically set a maximum value, and if it's over that maximum value, you set it to the max value. Okay, so let's say that we have, let's say let's say the doors. Okay, let's say that we have the doors variable. Okay, and what we're going to do is that we say that if there's a house with doors that have more than 10 doors, okay, any house that has 10 doors, so let's say a house has 20 doors, we then set it to be 10. Okay, so we set it equal to the maximum value that we set. So in this case, we're not deleting it, right? We're not deleting it, but we're censoring it. Okay, so censoring just means that you just set it to the max value that you want. Okay, yeah. So you set a max value, anything above that, you just set it to be the max. Okay, data leakage, right? So data leakage means that there's some information from the, there's information that's being leaked into the training set, right? So that could be test leakage, right? So information from the test set is leaking into the model. Target leakage, so the target variable, the Y variable, is leaking into the data set. Okay. Okay. So this is week 4. Yeah, okay. This is week 4, and we're doing classifications. So here there are a lot of things here. So classification is not exactly very difficult. And metric. Right, so metrics are different ways to measure the model performance. Right, and there are many metrics you can use. You can use accuracy. You can use the error rate, or you can use the precision, specificity, stuff like this. Okay. Okay. Specificity, precision. Okay. And I didn't explain this in I didn't explain this. I don't think I explained it this semester, but I might be wrong. But this is a very typical kind of machine learning interview question. Okay, and I say that suppose I have a model, and the model is 99% accurate. Okay, the model is 99% accurate. Okay, question is this model a good model? And if you're a simple modeler, okay, you may say that this is good, this is very good. Okay, the problem with this is that it's heavily dependent on your data set, right? And if your data set is imbalanced, this number can mean nothing, right? Because if your data set has 99 zeros, it has 100 data points, right? 99s are true, right? So this case, right, this week we had a lot of legit transactions and one false transaction. Okay, so in this case, your model can just predict legit, right? So the model just predicts legitimate every single time, right? And it doesn't even look at the data set. Okay, it doesn't even look at the X variable. All it does is that it just predicts legitimate every single time. Okay, and still your model will then be 99% accurate. Okay, and that's the reason why you need to look at the precision, the specificity, stuff like this, because you'll see that this has a precision of, specificity of 0, something like this. Okay, so that's the reason why accuracy is not always a measure that you want to look at. You want to look at also the specificity and other stuff, especially when you have imbalanced data sets. Okay, especially when you have imbalanced data sets. Okay. Okay, so we have the Bayes classifier here. Okay, and the Bayes classifier is perhaps the most misunderstood ones. Okay, so this is one of the discussion forums. Okay. The naive Bayes classifier is not the same thing as the Bayes classifier. Okay, these are not the same things. Okay, the Bayes classifier is the most optimal classifier. Naive Bayes is not. Okay, and perhaps a better way of writing the Bayes. So what is the Bayes classifier then? Okay, is that we just start from Bayes theorem. Okay, and Bayes theorem is this, right? This is just math, right? So we didn't do anything magical here. This is just math. Okay, we'll say probability of class given data set is equal to data set given class, class given data. Okay. Now in the Bayes classifier would be if we know what this probability is, we know this probability, we know this probability here. Okay, so if we want to make this prediction here, we need to find these 3 things. And if you can find all 3 things, then you have the Bayes classifier. Okay, so the problem is that this thing here, okay, this is usually very difficult to estimate, almost impossible. So we consider it a theoretical classifier. Okay, so you can see here. Oh yeah, we don't. Yeah, but we typically consider the Bayes classifier as a theoretical classifier. Okay, because this thing here is just so difficult to actually get. And what the naive Bayes model do, what the naive Bayes does, and what LGA and QDA do, is that naive Bayes makes assumptions that your data sets is independent from each other. And that's it. Okay, so that's the key, is that naive Bayes just makes the assumption of independency. Okay, that's it. So because it's independent, then you can split up those classes here. So you can split up that thing. So you can split up the data set into these things. Okay. And that usually, and these things tend to be a little bit easier to solve. Okay. And key difference between LGA and QDA, and in LGA and QDA, right? So in Gaussian discriminant analysis, you make the assumption that this is a normal distribution, right? You make the assumption that right, that the X given Y Okay, so the data set, basically, the data is X, class is Y, right? So you make the assumption that this is a normal distribution. Okay, and of course, you should know the difference between LGA and QDA. Okay, and I go in more details in this in the week 4's Q&A. Okay, so if you want more on that, just watch that. Okay, so be very careful with the difference between the Bayes classifier, naive Bayes, and stuff like this. Okay. Right, and then now we have in classification we have 3 things, right? We have logistic regression, we have LDA, QDA, and k-means k-nearest neighbors. Sorry, right? And the key is that LDA and logistic regression, these can only fit linear decision boundaries, while QDA and k-nearest neighbors can fit non-linear decision boundaries. Okay, and of course, right, sorry, and of course, because these are linear decision boundaries, they're less flexible. Yeah, they're less flexible, right? They have low variance, high bias, kind of, and because these can fit non-linear decision boundaries, and k-nearest neighbors can as well, these tend to have high variance but low bias. Okay. Right. Yeah. So confusion matrix is very important, especially when you have imbalanced data sets. Okay. It's one of the most important metrics that you need to look at. Okay. Yeah, imbalanced data sets. Right. There's also a trade-off between sensitivity and precision. I wish I was able to explain this more, but honestly, we didn't have much time. I don't even have time right now. Okay. So I'll probably go over time, but that's fine. But yeah, don't get tricked with accuracy. Okay, you need to think about the data set as well. Okay, so here we have this risk, and the risk is basically the expected loss. Okay, so the expected value of the loss between the y variable, I guess, and a, which is your action. Okay, and what you want to do is you want to find the action or the policy such that it minimizes the expected loss. Okay, and this is the expected risk. Okay, the expected risk. Okay, we want to minimize the expected risk. Okay. Okay, yeah, we did this. I think this was in the first tutorial that we did math. Okay, so you can probably look at that. Right, exemplar-based methods are based on the similarity between the input and the training set. Okay, so examples of exemplar-based methods will be k-nearest neighbors and locally weighted regression, right? Because in local regression, you need to compare it. Right? You're basically looking at your neighborhood and only performing the regression inside that neighborhood. Okay, and outside the neighborhood, you leave it alone. Okay. Parametric models can be thought of as a finite. You have a finite number of parameters, but non-parametric models cannot be indexed by a finite number of parameters. Okay. So perhaps a good way of thinking about it is the number of things you need to remember grows with the number of observations. Okay, so if you have more data sets, non-parametric models need to remember more, parametric models don't. Okay, it just stays the same. So in linear regression, if you have more data, you just remember the coefficients, right? You have 4 coefficients, you just remember the 4 coefficients, even if your data set gets bigger. But in k-nearest neighbors and in local rate regression, right, you need to, if your data set increases, you need to remember all that data set because you now need to find the neighborhood inside that entire data set, okay, every time you do it. So that's the key difference between parametric and non-parametric is that basically the number of things you need to remember, how does it grow in terms of the data set. Right, so parametric, and know the difference between parametric and non-parametric, right? Why parametric is good, why non-parametric is better, right? Parametric is good because they're less flexible, but quicker to train, right? More stable and more interpretable. Non-parametric models are more flexible, but more difficult to train, less stable, less interpretable. Okay. And you know, we see this, right? Local regression is very flexible. Okay, so this is a key thing. So empirical risk minimization. Okay, so there was a question that I saw, not in this course, but I think in the interview question somewhere. But they say, why is it called empirical risk minimization? Okay, why is it called empirical risk minimization? Okay, it's called empirical risk minimization because what you're minimizing fundamentally, right, is that you want to minimize the risk, right? Yeah, that you want to minimize the expected loss, which is the risk. Okay, it's called empirical though. It's called empirical because it's based on the observations that you have. Okay, so rather than right, the problem is that we don't know what the expectation is. Right, the expectation is basically when you have an infinite number of data points, but we don't. Right, we only have, you know, let's say 100 data points. And so why we call it empirical is that we just take the average over the data set. Okay, so that's why they call it the empirical risk minimization, is that you're minimizing the risk. Okay, you're minimizing the risk, but it's the empirical risk because it's based on the data set. Okay, so whenever you hear like empirical mean, empirical something, all that means is that the mean, right, the theoretical mean is when you have an infinite number of data points, but the empirical mean is just on the data set. Okay, so yeah. Blah, blah. Right, overfitting and bias trade-off, right? Most fundamental, most fundamental thing that we have, right? So make sure you understand the bias variance trade-off, right? That if you have high bias, you tend to have low variance. If you have high variance, you have low bias. Okay, and if you have high variance, low bias, it means your models are more flexible. Okay, but if you have low, I don't remember what I'm saying anymore. If you have high variance, you have low bias. Okay, which means your models are flexible. Okay, if you have low variance, you have high bias. Okay, which means your models are not flexible. Okay, so it means that the model can't move as much. Okay, very fundamental, right? Make sure that you know that instantly. Okay, underfitting occurs when the model has too high of a bias. Okay, so right. So we have overfitting and underfitting, right? Overfitting would be when the model is too complex, right? So the model has too low of a bias, so it's moving all over the place. Underfitting would be when the model is not fitting the data set correctly. Okay, so it's not fitting it correctly. So this is overfitting, right? So it's all over the place, and this is underfitting. This will be underfitting. Okay, so it's not correctly fitting the data set, and this is fitting, right? So it's just right. And it's important to know the difference, or it's important to know how you can spot these two things here, right? So in overfitting, overfitting is good in test, right? So it's good in train, but bad in test. Okay, but underfitting is bad in train and bad in test. Okay, and then the perfect amount would be good in train and good in test. Okay, but these are the ways that you can identify underfitting and overfitting. Is that overfitting is good in the train but bad in the test. Underfitting will be bad in the train and bad in the test as well. Okay, so just keep that in mind. right? So yeah, can memorize this feature. Okay, so that's basically what I'm saying. Is that when you're underfitting, you have a bad train, you have a bad generalization. But when you're overfitting, you have a good train but bad generalization. Okay, so bad validation. Right, how to avoid overfitting? Right, regularization, feature selection, model ensemble. Right, so just ensemble models together. Right, yeah. So this is a good example of model that's high bias. Okay, so the model is the data point is like this, but you're just fitting it over here. Okay, this is a high variance. Okay, it's just all over the place. Right. Right. Make sure you know the cursor. Make sure you know the cursor dimensionality, right, which basically means that as you have as the dimensions increase, models sometimes perform worse. Okay, exponentially. K nearest neighbors is one of the worst examples for this. So suffers from this the most. Okay. I guess the dimensionality reduction, by the way, this is also feature representation, right? Because rather than representing it with a whole bunch of features, you choose to reduce the dimensions, right? So you're reducing the way to represent the data set. Okay, yeah, I'm going way too slow. Okay, right. Right, so model selection, right? So we have, right. So there are three ways to do model selection, right? Very important. We have validation set, cross-validation, analytical criterion, right? I assume we know these two. Okay, I'm not going to go through these things here. The difference between analytical criterion and these things here is very different. So this is the right, and also make sure you know make sure you know what's good between cross-validation and k-fold cross-validation. What happens when you increase the number of Ks, right? What happens when you increase the number of folds? Okay, right. Yeah, so basically, if there's a method, always remember, or at least know what's the positive and what's good and what's bad. Okay, and that's generally going to be a good idea. Okay, so this AIC and BIC scores. The difference between AIC and BIC compared to cross-validation is that it's how we train our models, basically. Okay, in the cross-validation set, right? Let's say this is my training set. This is the full training set, right? And this is my test. In the cross-validation framework, we take the training set and then we split it into the train and the cross-validation fold. Okay, we train on the training set and then we evaluate on the cross-validation. And then we pick the model based on the cross-validation error. Okay. The AIC and BIC is very different. Is that you take this, okay, take this test, take the train, you take the training set, can you train the model? Okay, so you take the training set, you train the model, and then you evaluate the AIC or BIC. Okay, but in this cross-validation fold, you're just training it on the training set and you're predicting on the cross-validation set. Okay, so there's a very big difference between these two. Is that what you do is that in the AIC is that you compute the cost. So you train the data, you train the model on the training set. So no splits. You just train it on the training set. You do that, and then you just plus 2, and you just plus 2 multiplied by the number of parameters. Okay, and that's it. Okay, same thing for BIC is that we're just doing the same thing. Okay. But yeah, they're less applicable than the validation set approach because they're based on theoretical assumptions. Okay, but so that's the key difference between them two. Right, is that, yeah, okay. So we have hyperparameter optimization, right? I'm not going to go through this because we did this all the time. grid search, random search, Bayesian optimization, right? The key between Bayesian optimization and these things here is that Bayesian optimization, you're using previous trials to inform your future samples or your future trials. Okay, but these ones you don't just search through it. Just search through the place. Okay, model stacking, ensembling, model average, choosing models, model averaging, model stacking, model evaluation, test sets. Right. Yeah. Also, the test set, right? So the test set should be an unbiased estimation of the performance. Okay, so I explained this in one of the tutorials, but you should never use a test set. Okay, you should never use a test set to basically perform the cross-validation, right? Is that, yeah, you don't want to use a test set to perform the cross-validation, because what that does is that it leaks information from the test set, basically. Okay, so there's information leakage, I guess. Okay. Okay, maybe this might take 2 hours, who knows? Okay, so there are these 3 methods. So filter method, wrapper methods, and embedded methods. Okay, so filter methods means that you're selecting the features before you learn the algorithm. Okay, so filter methods will basically be like, like you only use the predictors that have higher than have a correlation higher than 20%, right? Or like has a higher 5K than, I don't know, 2 or something like this, right? Or like something. Okay, so basically, even before you train the algorithm, you're already removing the features by some sort of criterion. The problem with this is that features that look irrelevant by themselves may be relevant in total. Okay, so just because it's by itself, it looks useless. But sometimes when it's combined together, okay, so when you combine it with a new variable, then it actually may become useful, that both of them become useful. Okay, so that's one issue with filter methods. Wrapper methods is then you're evaluating the learning algorithm with different subsets of the features, right? So you take some subset of the features, you train the model, you get a new subset, you train a model, you get a new subset, you train a model. Okay, so here you're actually training it on different you're training it on different versions of the data set, right? But here you're selecting the data set even before you train the model. Okay, embedded methods would be feature selection is a part of training. So this will be lasso and ridge regression, right? That by regularizing the model, you're setting some of the features to equal to 0, or you're shrinking the impact of the features, right? And that will be an embedded method. Okay, right. So best subset selection would be an example of wrapper selection. Right, recursive feature elimination. Yeah, you're training the models with all the features and identifying the weakest feature according to some measure of feature importance. Right, and we have k-nearest neighbor. Sorry, random forests have feature importance that we can do that with. Right. Yep. So regularization will be an example. So yeah, these will be an example of embedded methods. Okay. Oh yeah. Also, be careful between the difference between the shrinkage factor and the regularization strength. Okay. Right. A higher lambda increases the shrinking factor. Okay, so if the shrinking factor increases, right, so as lambda decreases, so as the regularization strength decreases, the shrinkage factor increases. Okay, it goes from 0 to 1. So as lambda decreases, the shrinkage factor increases. So therefore, as the shrinkage factor decreases, so I guess as lambda increases, the shrinkage factor decreases. Okay, so they go in opposite directions. Okay, so just be careful about that. Right. yeah, and make sure you know the difference between ridge and lasso. Make sure you know the benefits, what's good and what's bad with them. You know, when ridge regression, when lasso regression is good. Make sure you know e-net regression. You know why. You know, e-net regression is basically like a middle ground between um, both of them. Okay, and right, and we have these kind of ways to, I guess, interpret the model, right? So we have these like partial dependency plots, and we have these sharp values. Okay, and I explained this in the recorded Q&A for this week, so I might want to look at that there. Okay, but these are basically model agnostic interpretations. So there are ways to interpret the models. You know, like looking at the coefficients is only possible for linear regression, but you can't look at coefficients for tree methods. Okay, there is no coefficients. So instead, you need to look at these model agnostic type of ways. Okay. So we have GAMs, decision trees, random forest, boosting neural networks. Sorry, what are we doing here today? Right, so we're modeling nonlinear ways. Right, so this is representation learning. Well, this is more or less representation learning, right? Because what you're doing is you're taking your input, you're putting it through a function, and you're learning that function. Okay, so if we go back to here, so we take windows, and we put the number of windows through a function. Okay, so this function can be like, let's just say the function is, okay, make it simple, okay? So we say the function of x is equal to, let's say, log of x. Okay, I don't know, maybe you did the GAM and the GAM generalized additive model, and the GAM gave you a log. Okay, so in this case, your representation of windows, so the way that you're representing windows is actually the log of windows. Right, so f of windows is equal to log of windows. Right, so instead of using windows, your representation of it is actually the log of windows. Okay, so right, and this is probably another example of representation learning. Okay. Right, polynomial regression, again, another example of representation learning. Right, make sure you know the difference. You know, polynomial regressions tend to be very, very flexible. Right, basis functions, this is a little bit more difficult for me to explain. Yeah, it's a little bit more difficult for me to explain. Right, and we have regression splines. So, you know, I explain regression splines very, very thoroughly in the tutorial of this week. Okay, so, you know, I explain what a cubic spline is and a natural cubic spline. Make sure you know the difference between these two, right? Yeah, make sure you know the difference between a cubic spline and a natural cubic spline. So watch the tutorial if you don't know that. A natural spline. Right, smoothing splice. So we'll talk a little bit about this in the recorded tutorial. Right, so what happens when lambda is equal to 0? What happens when the second derivative is equal to 0? Stuff like this. All right, local regression. Again, you know, local regression has a very good idea of, rather than performing regression over the entire data set, why don't you perform regression over, you know, my neighborhood? Okay, and you can use different kernels to basically weight your thing. Right? And this is an example of exemplar-based methods, where exemplar-based methods means that you need to remember the data set, right? Yeah, you need to remember, or you're basically computing some sort of similarity in the data set. Okay, so example of exemplar-based methods. Okay, so the way that you fit GAMs is through backfitting, which I explained in the recorded tutorials. Right, and the key is that GAMs are only additive. Okay, GAMs is only additive. So you can see here you have fx1 plus fx2 plus fxp. Okay, so they're all adding each other. There's no interactions. Okay, an interaction is when you have you know, f of x1, x2, comma. Okay, and the way that you'll fix this in the GAM is by just simply adding, you know, some function. Okay, so p plus 1 of x1 multiplied by x2. Okay, so before you fit a GAM on x1, x2, blah 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 to xp. Okay, and now you just simply add another one where x1 multiplied by x2. Right, again, representation, right, is that rather than representing it with just these p variables, you do it with p plus 1 variables. Okay, where the last representation is a multiplication. Okay, and you just fit a GAM on the multiplication between the variables. And that will be and that is how you can introduce interaction effects with in GAMs. Okay. Okay, now we're going quicker because we basically, I talk about, in the tutorials, I talk a lot about trees and bagging and stuff like this. Okay, so you should probably refer to the tutorial. You should probably refer to the tutorials for bag trees, boosting and stuff like this. Okay, sorry. Yes. But yeah, so just like in k-nearest neighbors, right? In k-nearest neighbors, you should know how to make a prediction if you have a data set, right? If you have a data point, you need to know how to make a prediction. And same thing for trees, right? Is that you have a data set where, let's say the qualities, okay, you have a data point, right? And you need to just go down the tree. Okay, so this was a quiz question, I think. Right, and make sure you kind of know the idea of growing a decision tree. So like, maybe knowing every single line by line is not exactly very important, but understanding the general idea, right? Is that you take a node, right, or you take a tree node, and you just you split on one of the variables, right, and you choose the variables greedily, right? So you you choose a split based on what gives you the best results. Okay, so you do it greedily. Yeah. And you can measure the quality of a split by using the node impurity measure. This is really, so the Gini index or entropy, and this is really for classification. Right, what's cost complexity pruning, right? Again, trees very notoriously, right? Trees can overfit very easily. Right, and how do you fix overfitting? You regularize the model, right? And in this case, in trees, the ways that you overfit is if you ask too many questions, right? And so we regularize the model by putting a penalty on the number of questions that you ask. So effectively, the number of root nodes that you have, right? And the more root nodes that you have, right? So yeah. Okay, so if you have a lot of root nodes, it means you're asking a lot of questions. So we penalize you for that. Okay. All right, and we find it alpha to minimize that cross-validation error. Okay. Right, make sure you know the advantages of trees, the disadvantages of trees. Right, bagging, very, very cool idea. The idea of bootstrapping, right, where you sample with replacement. Right, again, I explained this in the tutorial. Right, and the difference between pasting, right? So pasting is you're sampling without replacement. So in bagging, you take one, you put back in, take one, you put back in. Pasting, you take, then you take, you take, you take. Okay, you don't put it back in. Okay, and the difference between random forests and bagging, right, is that random forests, you now add that you can only use a certain amount of predictors at each split. Okay, and that decreases the variance, right? Right. Right, and as with each model, you should know the kind of like general idea of the bias and variance, right? Like you don't need to know exactly the exact details, but a tree tends to have, well, if the tree is very small, right? If you have a small tree, you have what do you do? So if we look at this, so we look at the bias, variance. If we have a small tree, Okay, then this maybe like 1 or 2 layers, two depth. Okay, this will have a high bias and low variance. If you have a big tree, like a very, very big tree, you have a low bias and high variance. Right, then comes random forests and uh, bagged trees. So let's say bagging and random forests. Right, of course, because you're ensembling, right, this now increases your bias slightly. So you have a slightly higher bias, but you have a dramatically lower variance compared to these trees here, right? And then, as I also said in the tutorials, when comparing to boosting, if you boost too many times, okay, if you boost too much times, you tend to have a lower bias and high variance. Okay, it's just a little bit slighter. So not too much, but just a little bit more. Just a little bit more. Okay. So boosting. Right. So honestly, there's not really much we can say here. So, boosting, if we think about gradient descent, right? If we think about gradient descent, gradient descent, right, is that you're taking the parameter at the m-1 step, and you say this is equal to this subtract by the learning rate multiplied by the gradients at time m. Okay, so that's effectively what you're doing in these least squares boosting and gradient boosting, is that you're taking the parameter at time m-1, but in this case the parameter is now a function. Okay, so that's the thing that's kind of weird about this, is that we typically think of a parameter as a number, but now the parameter is a function. Okay, so this is very weird. So basically what this means is that you're moving in function space. Okay, but when you have parameters, you're moving on the real number line, right? So you have your x-axis, right? So you have you have an axis, and this is data, right? So when you're moving, you're just moving on this axis. But what we're doing here, when we're doing these things here, we actually have a function space. So this is a space. Okay, it's like a cloud that has all possible functions in it, and you're moving from function to function to function. Okay, whatever that means. Okay, very, very, very weird concept. Okay, but that's effectively what we're doing here, right? Right, yeah, and also I also explained least squares boosting in the tutorials as well, so go check that out. We have some hyperparameters, right? It's the number of trees. So the number of trees is basically the number of epochs that you have, right? Or the number of times you descend down the gradient, right? The learning rate is how quick you want to descend each time, right? Of course. And in boosting, we set the max depth of each tree to be small, right? So we typically set them to be small, because the idea in boosting is that we want to create one good classifier from multiple small classifiers. Okay, so we're building we're using weak classifiers to build one strong classifier, right? So strength in numbers, right? And early stopping. So I also explained this in the tutorials, but the idea is that you don't want to keep boosting, right? Because in neural networks, training takes a long time, very, very long time. Okay, so you think about gradient descent or Newton's method, right? These things can take a very, very long time to train. And so what you want to do is that you want to stop if you think you're starting to overfit. Okay. And you can use early stopping for that, which is you go down, and if you think you're at a minimum, okay, so if the cross-validation error starts to increase, you continue to train, and you only stop if after 30 training rounds, after 30 iterations, you don't get a better result. Okay, and that's early stopping, right? And of course, know what's good about early stopping, what's bad, right? Early stopping can reduce your training time. But what's bad about it is that you can get stuck at a local minimum. Sorry, you can get stuck at a local minimum. Okay. right? And gradient boosting, okay, so this is not clear here, but if you watch the recorded tutorials, it's very, very clear. So yeah, actually here. So you can see here that when we are, right, so we're computing the gradients, and then we fit the trees to these gradients. Okay, so we're actually modeling the gradients, and then we then descend down the gradient. Okay, so that's what we're doing here, is that we just descend down the gradient. And this should be a minus, okay, but it's because we have the minus there, because we're modeling the negative gradients. But essentially, right, all you're doing is that you take your time n-1 and you're subtracting by the gradient, okay, which is just what you're modeling here. Okay, so just exactly like linear gradient descent. And that's XGBoost. So that's gradient boosting. And XGBoost comes with an idea of adding regularization. So penalizing the complexity of each trees, right? So you're adding some regularization. So it's gradient boosting plus some regularization. Right, and the difference between level-wise growth and leaf-wide growth, which is what LightGBM does, but XGBoost does level-wise growth, right? So in XGBoost, you're growing each level, right? So in XGBoost, you by necessity, so the next step of XGBoost would be like this, right? Then like this, then like this, then like this. Okay, so you're growing each layer. But in what the hell? But in leaf-wise growth, you can just grow by each leaf. Okay, so you can see here, we have the 1, 2, 3. So we have the third layer, right? So we have the third layer, even though the second layer isn't fully built out yet. Okay, but in level-wise growth, you need to fully build out that second layer before you can begin this layer here. Okay. It's a big difference between them two. Okay, almost there. Right, so we have regularized risk minimization. So we're looking at likelihood functions. So yeah. So just be careful. This likelihood function is not a probability distribution. Okay, it's not. And I understand that I explained it almost like as if it is a probability distribution. I understand, like if you go back to the recordings, I explain it almost as if it is a probability distribution, but it kind of is, also kind of isn't. I guess it kind of is, but also kind of isn't. Yeah. So, but that's just to note, okay, that the likelihood function is not a probability distribution. Yeah, so it's kind of this weird concept, but just keep that in mind. Okay. Right, maximize the likelihood estimator. Right, and effectively what we're trying to show here is that if we think that the data set given the parameter, okay, so if we think that the distributions of each y variable, okay, so if you go back to the recordings, it might make sense if you rewatch that. But if we think about the probability of the data set given my variable as a Bernoulli distribution, so if we think about it like this, okay, what effectively we're showing here, right? So this is the likelihood function, right? This becomes the likelihood function if we assume it's a Bernoulli distribution. What we're showing here is that the log likelihood, okay, which is this thing here, okay, what we're showing here is that the log likelihood is equal to the binary cost entropy loss function, right? So the binary cost entropy loss function corresponds, so when you're doing classification, what you're minimizing is that you're minimizing the cross entropy loss function, right? The binary cross entropy loss function. And what we're showing here is that the binary that minimizing that, okay, so minimizing the binary cross entropy loss function is equivalent to the maximum likelihood estimator of when you assume that the y variable is a Bernoulli distribution. Okay, so if you go back to this tutorial where I talk about Minecraft and I talk about Dream cheating, and we computed his blaze spawn fire rods probability, right? What we saw was that the ratio of the number of drops over the number of samples, right? So that's the number of blaze rod drops over total a number of blaze killed. Okay, so this is just the fraction of the number of blaze rods that were dropped over the total number of blazes that were killed. Okay, and what we showed is that this is equivalent to the maximum likelihood estimation of the data set. Okay, so that's really why maximum likelihood is so cool, is that even in such simple concepts of the proportion, okay, the proportion, it turns out, is actually the maximum likelihood estimation. And that's exactly what we're doing here. That's exactly what we're showing here, is that the binary cross entropy loss is equivalent to the maximum likelihood estimation when we think that our data set is Bernoulli distributed. Okay, so a very, very powerful thing here. Okay, yeah. Also, maximum likelihood is efficient, is consistent, is asymptotically efficient, right? So consistent meaning that as you have an infinite number of data points, you get equal to the true value. Okay, and it's asymptotically efficient, meaning that it has lowest variance amongst all consistent estimates. The key is consistent. Okay, it has lowest variance among all consistent estimators. Okay, so that doesn't mean that it has lowest variance, but it has lowest variance among the consistent estimators. Okay, so this is another thing that people say, is that the OLS solution, so the OLS solution, which is right, so this formula here is the maximum likelihood estimator, which has the lowest variance amongst all the consistent estimators. Okay, but we know, right? So that's the OLS. So just say normal OLS. But we know that ridge regression, lasso regression, and everything else has lower variance than this thing here, right? It has lower variance than the normal OLS solution. Okay. This seems kind of weird because this is saying you have the lowest variance, but the key is that it's the lowest variance amongst consistent estimators. Okay, so it means that the unbiased estimators. So as you have an infinite number of data points, if you have an infinite number of data points, then the coefficients will converge to the true data points. But in ridge regression, you have lower variance. But if you have an infinite number of data points, you don't approach the true coefficients, right? Because you have a bias of making them smaller. Okay, so that's kind of like a little bit tricky here, is that it has the lowest variance, but only amongst consistent estimators. But typically regularized models will tend to have lower variance, right? So ridge regression has lower variance than normal regression does. Okay, but it's not consistent. So that's the key. Okay. And here we're talking about basic optimization procedures. The first derivative is equal to 0, second derivative is greater than 0. Honestly, this is just some math, right? So you're guaranteed to have a strong minimum if the first derivative is equal to 0, second derivative is positive. Okay, and just note, if the second derivative is equal to 0, the point may or may not be a minimum. Okay, so basically, if you think about y is equal to x cubed, and the second derivative is equal to 6x. Okay, and y prime prime at 0 is equal to 6 times 0, gives you 0. Okay, but the problem is, so you have second derivative is equal to 0. And what happens is that this is how the cubic function looks like. Right, so at 0, it's just flat. right? So you need to be a bit careful with that. Okay, so that's why if the second derivative is equal to 0, it may or may not be a minimum because you might have that point there. Okay, then we have a convex function. So the easiest way to understand a convex function is that if you draw a line segment between any 2 points of the graph, then it does not lie below the graph between the 2 points. Okay, the line segment does not lie below the graph between the 2 points. Okay, and that will be a convex function. So if we think, maybe, this is non-convex, right? So this function here is non-convex, right? Because we have one minimum, we have another minimum here. And this is saying if we choose any 2 points, it must lie above the line. Okay, so if we choose 1 point here, we choose 1 point here. Okay, because at any point, right, we can see that we do go under the curve. Okay, but if it's convex, then for any point you choose, okay, for any 2 points you choose, that line will always be above the function. Okay, always be above. Okay, and I'm going to just like rapid fire through this because it's 2 left. Everyone's tired. I'm tired. Right, and then we have multivariate conditions where for it to be a minimum, you need this thing to be positive semi-definite. Okay, so whatever that means. Okay, whatever this means. Okay, and then we looked at local descent methods, right? And we're looking at Newton's method. Okay, so it's kind of a little bit tricky for me to explain that right here, but basically Newton's method is based on a second order Taylor approximation. Okay, so that's it. Okay, so it's based on the second order Taylor approximation. Okay, but Newton's method is basically the first order. Sorry, Newton's method is a second order. Gradient descent is basically the first order. Okay, so that's more or less what's happening here. Okay, and make sure you know the difference, what's good and what's bad about Newton's method versus gradient descent, right? Newton's method in general requires less iterations. Okay, but when you have a lot of parameters, the computational cost just gets huge. Okay, in contrast to gradient descent, where it might take you more steps. Okay, and you also have a hyperparameter to choose from, right? You need to choose that learning rate. If you set the learning rate to be too high, you don't even converge, right? As we see in the tutorials. Okay, and you need to make the learning rate small. Yeah. Okay, and can be sensitive to the scaling of predictors. Oh yeah, I actually showed this in the Q&A session. Okay, so yeah. And know the difference between stochastic gradient descent and gradient descent. So in gradient descent, basically by definition, gradient descent is computing the gradients over the entire data set. But in batch, you're only considering random subsets of the data set. Okay, random subsets. So that's the key difference. And then stochastic gradient descent is when you're only using one data point, but batch is when you're considering multiple data points. Okay, and of course, what's the benefits, what's good and what's bad. If you're using one data point, it's quicker to compute the gradients, but tends to be a lot more noisier. If you're using batch gradient, it takes longer to compute the gradients, okay, because you need to compute multiple, but tends to be less noisy. Oh yeah, sorry, let me just. Okay, so honestly, if you're confused with this tutorial, I would suggest just watching a YouTube video, to be honest. So if you want more information on neural networks, I would just suggest watching a YouTube video, because there are a lot of YouTube videos, huge, like so many, like there's like 3 blue, 1 blue, brown. Yeah, this guy. Okay, so this is a pretty popular guy. He does a lot of neural network stuffs. Okay, whatever. And gradient descent, right? So there are, yeah. And these people, they have a lot of time to animate their videos, right? They take a long time to create the videos, so it's a lot more visual. Okay, and these videos gets millions of views, okay, 10 million views. We don't have that much time to create these things. Okay, but one fun fact. Okay, one fun fact. So I thought, I was a simple kid, so I thought a neural network meant if you have multiple layers, right? So I thought a neural network just means that if you have like layer, and then that goes into a layer, which goes into a layer, which goes into a layer. Okay, so you have this like, I thought this was a neural network. Okay, it turns out that neural network only refers to the situation when you only have one layer. Okay, when you only have one hidden layer. And a deep neural network refers to the situation when you have multiple hidden layers. Okay, which to me is the most yeah, it's whatever it is. Okay, it's whatever it is. Okay, but apparently that's the difference between a neural network and a deep neural network, is that a deep neural network you have more than one, neural network you have one. Okay, so this is the same thing as stochastic gradient descent. I thought stochastic gradient descent is when you're just using multiple data sets, but it turns out stochastic refers to only one data point. Okay, so you'll need to, because you're a student. Okay, I'm not a student. You need to suffer through this, but because I'm not a student, I can get it all wrong. Okay, but that's because I'm lucky. Okay, all right, cool. That's that for me. If there's any questions, feel free to let me know. Otherwise, yeah, it was fun. I had a lot of fun. I hope some people had some fun, learned something along the way. And yeah, yeah. If there's no questions.
Yes, hi James.
Yeah.
Yes, I want to ask a question about the GLMME. That's the target encoding in tutorial 3.
Yeah.
Yes. So would you mind if you can open the notebook in that week?
What week is this?
Tutorial 3 notebook. Yeah, that's what we learned that week.
Just give me 1 second.
Okay, thank you.
Oh, no. Blah, blah. Tutorial 3. Okay, yeah. What's the question?
And about the target encodings.
Yeah.
Yes. So after we do the target encoding, we group by our new features and compared it with the original ones. So we compare neighborhood and neighborhood GLMM, right? But I am a little confused why we do that.
Sorry, so you confused neighborhood GLMM and what?
And the original data, just the graph below it. The group by, yes, this one.
Oh, okay, sorry. Oh, you confused this. Oh, okay, so what this one shows is that okay, so for each Oh, okay, sorry. Yes, that's right. Yes, yes. So what this is saying is that no ridge, okay, so just ignore this code for a second. What this is saying is that the encoding for no ridge is that no ridge has a value of 0.7, nridge has a value of 0.6, IDOTRR has a value of negative 0.56, something like that. That's what you're showing here is that, that's what this is saying. And then you can do the same thing for other encodings. Okay. Okay, I don't show it. But yeah, sorry. Yeah, so yeah, that's basically what that does is that what's essentially if you watch the recorded tutorial, what at least what Lee1out does is that it basically takes the average of the y variable, right? So you look at the no ridge and you look at the prices for the no ridge houses, and you're basically taking the average of those houses, right? And so what you're doing is that you're substituting no ridge as the average house price for no ridge. Okay, and that's basically more or less what GLMM is doing, is that it's taking no ridge and it's substituting it for 0.06, nridge hat substituting it for 0.5 and so on. Okay, so that's what's happening.
So it means maybe when if you are in if you are the no ridge you are 0.6 higher than the average price.
I wouldn't say this is not quite true for GLMM. For GLMM, it's just kind of no ridge is most valuable. Nridge has the second most valuable, and these are just very, very bad. So that's really what this is. Yeah. So it's kind of like a scale.
So it's like the negative side means they are lower than the average level, right?
Yeah. Yeah.
Oh, yeah. Thank you.
Yeah. All good. All right. Cool.
Hi, James.
Yeah.
I have a question about the safe graph, and I do the statistic model like linear regression results.
Oh,
and
yes. You can't convert it to a yes. I answered your question on it. You can't convert it to a PNG. You can only convert it to a CSV.
But I want to show the p-value in my report. So how can I do that?
You just put it in a table.
Oh, okay. Okay.
Yeah, just put it in a table. Yeah.
Oh, hello, James. Just a short questions. So for our assignment, do we need to include include how to install the package in our code?
No.
Just like what we do in the Google Cloud.
You don't need to explain the code in your assignments. No, you don't.
Okay, thank you.
Yeah. All right. Yeah. All right. Seems like there's no questions. All right. Bye, everyone. Was fun. Catch you on later. Skirt.